All right, let's dive right into this explainer. If you've ever tried running massive large language models in production, you know the absolute headache of bottlenecks. Today, we're unpacking something huge. Tencent Hunyuan just upstreamed their HPC-Ops kernels directly into the vLLM main branch. This isn't just some tiny patch, folks. We're talking about a fundamental re-architecture of high-performance attention and mixture of experts backends. It's literally designed to squeeze every single drop of performance out of NVIDIA Hopper architectures. Here is our game plan for today. First, we'll ground ourselves in the real-world serving challenge. Then, we'll unpack the two major technical updates, dynamic load-balanced attention and a fused MoE pipeline. After that, we'll run through some hard benchmark data on H200 GPUs, and finally, wrap up with the end-to-end system impact. Let's get to it.
Section 1. The Real-World Serving Challenge.
We really have to ask ourselves, when you're scaling up a behemoth like Tencent's 295 billion parameter Hi3 model, why is production LLM serving so ridiculously hard to optimize? I mean, if you run a raw Matwell throughput test in isolation, everything looks great. But as we all know, production does not happen in a vacuum.
The reality? Real-world traffic is just chaotic. It's not this perfectly uniform batch of identical tasks. We have to deal with unpredictable, continuous batching. That means inside every single batch, you're hit with mixed-length decode requests. One request might be chewing on 16,000 tokens of context, while the one sitting right next to it just started with 1,000. Throw in the sheer complexity of mixture of experts models where you're wrangling these incredibly small expert gems, and suddenly your system is completely bogged down. You get stalled schedules, massive kernel launch overheads, and your wildly expensive GPU compute is just sitting there doing absolutely nothing, waiting for the slowest task to finish.
Section 2. Dynamic load-balanced attention. So, how do they fix that first bottleneck? Well, the old way, a static split KV schedule, is basically a traffic jam where everyone is stuck behind the slowest car. Because the split degree is rigid, short requests stall out, while the long ones totally dominate the launch. It's just wasted GPU cycles. But the HPC-Ops approach? It uses dynamic load balancing scheduling. The workload literally adapts in real time to the actual batch length distribution. It perfectly saturates the streaming multiprocessors, completely neutralizing that heavy skew. They pulled this off in 3 really elegant steps to make sure 0 cycles go to waste. Step 1 is assign. A lightweight kernel chops every KV sequence into uniform 64-token tiles and packs them sequentially into CTA buckets. So a massive sequence gets split fairly and a tiny one doesn't hog a whole block. Step 2, compute. They use a persistent kernel grid. Because it's persistent, it just grabs task descriptors and crunches the attention continuously. No relaunch overhead whatsoever. Finally, combine. A tiny kernel reduces those per-chunk partials into the final BF15 output. Everything finishes at almost the exact same millisecond.
And to totally round out the attention backend, they overhauled the prologue phase. Usually, you'd run QK norm, rope, and your KV cache write as separate memory choking steps. Instead, their fused attention prologue, called HPCR rope norm, squashes all those separate launches into one single operation right out of the fused QKV projection. It applies QK norm and rope in the right order, writes K and V straight into the paged cache, and if you're running FP8, it spits out a per token per head FP8 query with its scale, so the attention kernel never has to requantize. Boom. Those brutal round trips to high bandwidth memory, entirely gone.
Section 3. A fused MoE pipeline. Mixture of experts faces a huge architectural wall during low latency decode. Because every expert only gets a tiny handful of tokens, the expert GMs are incredibly small. But the conventional multi-stage MoE setup treats them like massive operations. You have to route tokens, gather them into per-expert HBM buffers, run the gate-weight jam, do activation and quantization, run the down GM, and then finish with a top K weighted reduction. It's exhaustive. In decode, this chain absolutely buries your system in kernel launch overhead and intermediate memory reads. It's death by 1,000 cuts. The HPC-Ops solution? Just tear the whole pipeline down and build one fully fused, compact execution path. No more redundant overheads. Here's how this fused FP8 MoE pipeline actually comes together. First off, routing and index building happens straight in shared memory, which completely slashes global atomic pressure. Then, the gate-up gem reads the original tokens right through that routing index, entirely skipping that standalone gather step. It's super smart. And they use an occupancy-first execution model, meaning a single warp group handles both data movement and compute. Zero warp specialization needed. But the real kicker? They chain stages using programmatic dependent launch. This overlaps kernel launches to literally erase the bubbles between stages, keeping intermediates and launches totally off the critical path.
Section 4. Benchmarking on H20 GPUs. Let's look at the payoff.
2.95x. That is the massive speedup the dynamic attention scheduler hits over a static split KV schedule on highly skewed, mixed-length batches.
When you break down the exact latency, the advantage is glaring. If you have uniform, small requests, sure, dynamic and static perform about the same. But the magic happens when you introduce a massive skew, say one request with 128K context mixed with 31 requests at 4K. The static scheduler just chokes on that, taking 0.186 milliseconds. The dynamic scheduler handles the exact same workload in just 0.063 milliseconds. As the batch gets weirder and more skewed, the dynamic scheduler just crushes it, averaging well over 2 times faster than both flash infer and flash attention.
Jumping over to the MoE backend, we're seeing an average 1.59x speedup at Tensor Parallel 8 compared to the best baselines.
To put that into perspective, at a batch size of 32, HPC-Ops clocks in at 124 microseconds, which drastically undercuts Triton's 184 and Cutlass's 275. This is absolutely critical because small to mid batch sizes completely dominate low latency decode. This proves the fully fused FP8 MoE pipeline drastically reduces latency where it actually matters. The hardware is finally being fed efficiently rather than constantly choking on kernel launches.
Section 5. End-to-end system impact. Let's bring it all together. When you deploy both of these optimized backends in a real-world serving environment, the end-to-end results on that 295 billion parameter Hi3 model across 8 H20s are wild. At a batch size of 16, time to first token drops from about 7,800 milliseconds down to roughly 5,885. That's a 24.6% improvement. And at a max batch size of 64, time per output token sees nearly a 30% reduction. You're getting roughly 30% faster generation overall just from swapping the backend.
But you know what the absolute best part of this whole explainer is? Every single optimization we just talked about is already merged into the vLLM main branch. Upstreamed as first-class backends, no compiling, sketchy, long-lived forks, no hacky integrations. You just use the native backend interfaces ready to go right now via standard pull requests.
And as the Tencent Hunyuan AI Infra team pointed out, this upstreaming is really just the start of their open source collaboration. They are pushing the boundaries of open, high-performance inference hand in hand with the community. Which leaves us with one final thought. With zero relaunch overheads, dynamic load balancing, and massive latency reductions directly available in stock vLLM today, how are you going to utilize these new HPC-Ops capabilities to scale your own production deployments? Are you ready to stop leaving so much GPU compute on the table?